Hello, my name is Angelina Dominguez, and I teach AP Computer Science Principles at Veterans Tribute Career and Technical Academy in Las Vegas, Nevada. I'm excited to be talking to you today about data compression. So let's look real quick about what we're going to learn. So we'll talk about data compression algorithms, specifically what it is and how it reduces the size of data. We'll compare different types of data compression algorithms. And finally, talk about situations in which you would use the different compression algorithms. So let's get started. Data compression is a reduction in the number of bits to represent data. We do this to save time and to save space. Storage capacity and network bandwidth always has limitations. So compressing data can save storage capacity, speed up file transfer, and even decrease costs for storage hardware and network bandwidth. Remember, every bit of data or information can be stored digitally, whether it's text, pictures, music, or video. All of it can be represented digitally, which means the information is represented on a computer by ones and zeros or on and off electrical signals. But representing information digitally can take up a lot of space. For example, let's say we wanted to store a 3-minute song. Well, that could take around 30 megabytes of space. And a 1 hour video could take like 800 gigabytes. So what happens is that digital information is compressed to take up less space. That 3-minute song could be compressed down to say like 3 megabytes. And that 1 hour long video could be compressed to be 1 gigabyte. When data is compressed, you're essentially looking for repeated patterns and predictability, redundancy in the data. So for example, let's say we have some X's and O's like this. We could compress this to be X3, O2, X2. Now, this might not seem like it shortened the information by much, which is true. But the larger the data file, the more patterns that can be pulled out from it. Text compression can be as simple as removing all unneeded characters and inserting a single character or even a symbol in its place, like this. If each letter is a byte of data and the original text contained 28 bytes, this was now reduced to 15 bytes of data, which means we just can compress this text by 46%. So let's look at some examples. So here's an example of a compressed piece of text, and here is the key to go along with that. So what I want you to do is pause the video and see if you can decompress this compressed text and recover the original. Unpause when you think you've got it. Welcome back. Did you get Humpty Dumpty? Awesome. So the original text was 142 bytes of information. The compressed ended up being only 80 bytes. But we also have to send this dictionary or this key along with the compressed text in order to recover the original. And the dictionary was 31 bytes, 1 byte for each letter and 1 byte for each symbol. So that made our compression rate about 21%. Now, the thing to remember about compression is that there's no one right way to compress. There's many compression algorithms out there, and each one works a little bit differently to compress the data. Now, pictures are a little harder. Coming back to this idea that what makes things compressible are patterns and predictability and redundancy. If you think about a photograph, some photographs do have predictable areas. You could take a picture of a small desert island in the middle of the ocean with a couple palm trees like this, and this is a little bit easier because the sky is smooth and basically one color, giving you thousands of blue pixels. You have hundreds of yellow pixels for the island, a few hundred more for the trees. So you can compress it not by sending every single pixel individually, but by saying there's the sky with the color blue, and there's 1,000 of those. just replicate them. Pull out these individual pixels and replicate them. The computer knows how wide the picture is, so the computer can just start duplicating the blue pixels in the right XY positions. You don't have to say, here's the specifications for blue pixel at position 1000, and here's the same spec for the blue pixel at 1001, and here's the same spec for the pixel at 1002. You don't need to do that. You just send the spec once and say, replicate it 400 times. Both of the methods that I just explained would be considered lossless data compression because the original data was compressed, or the original data that was compressed
can be recovered without the loss of a single bit of data. In essence, the dictionary is sent along with the compressed data file at the other end. The compression can then be reversed or decompressed, and we can recover the exact original data. Lossy compression, on the other hand, is a type of data compression where data is thrown out and cannot be recovered. This might be done with music files. Well, for example, like music,
there are sound frequencies that may be out of range for the human ear. So if we take those sound frequencies out that the average person can't hear and we throw them away, the file will be smaller and most people would never be able to tell. But imagine if we used lossy with a text file like this, and we had these words, food, fed, feed, feud, fad, and the compression algorithm threw out all the vowels. Well, we wouldn't really be able to tell the difference between these compressed words. So lossless data compression is the typical approach with executable files, as well as text and spreadsheet files, where the loss of numbers or words would change the information. Since lossy compression permanently eliminates bits of data that are redundant or unimportant or even imperceptible, lossy compression is used or is good to use with graphics, audio, video, and even images, where the removal of some bits of data has little or no discernible effect on the representation of context. A good example for lossy compression with images is the JPEG algorithm. You may have heard of the term JPEG before. It's a type of picture. It's many times necessary to get a photograph sized down in order to upload them and send them to somebody, or to upload them to an online storage site like Picasso or Flickr. Those sites are not going to be happy having every single one of your pictures taking up to like 20 megabytes and being utterly perfect. They want you to compress it down to kilobytes, as small as possible. Now, while there are some images out there that you could use lossless compression because they have patterns like that desert island in the ocean example, there are many other images out there that are just innately random looking enough that they are not easy to compress. So what the JPEG compression algorithm basically does is some really clever things, which make many parts of your images end up looking a bit blurry or fuzzy if you were to magnify them. Now it does this by dividing the picture up into blocks and squares and saying, well, the sky here on this picture on the left is almost the same blue across. It's a little bit darker on the left and it gets lighter to the right. So I'll just use an approximation. It takes those three colors or the colors of the sky across the whole sky, and it makes an approximation, and that's now the sky color, just one solid color. So if we were to zoom in to a JPEG, you'd see what looks like to be a blurry pixelated image. It's never recoverable exactly the way we started, but you get more compression this way, if you don't mind an approximation. And for most people, the human eye can't really tell the difference. And we'd think we were looking at something that looks pretty nice. So which type of compression is better, you might be wondering? Well, it really depends on your needs, as there are trade-offs for both. Lossy data compression can significantly reduce the number of bits stored or transmitted, but the original data can't be recovered or restored. On the other hand, lossless data compression does let you restore and recover the original data, but lossless compression usually cannot compress data as much as lossy can. So which do you choose? Well, in situations where quality or the ability to reconstruct the original data is important, well, you should choose the lossless compression algorithm. But if having the smallest data size or transmission time is what's most important, well, you should choose a lossy compression algorithm. Just remember that just because we're compressing data doesn't mean less information. In the case of lossless, we have a smaller data file, but the original can be recovered. And in the case of lossy compression, while there may be pieces of data that are thrown out to make a smaller data file, no actual information is lost as far as the human eye or the human ear can tell. So we reached the end. What did we learn today? So we looked at data compression and we saw how fewer bits does not necessarily mean less information. We looked at how data compression can reduce size. We also compared two different types of data compression, the lossless and the lossy. And we also looked at situations in which you would use the lossless or the lossy compression. So that's it for today. I'll see you soon. Bye-bye.